First, are there any questions about, we had a long break. Any of the last homeworks at all? You got it? Yeah, I was, did everybody get that assignment? Was it up there?
Yes, sir.
All right, and you did it?
I did it, but
Yeah.
I don't know if I did it right.
Yeah, why don't you pass that in? It would be for extra credit. And just can you collect them and put them up here? That shouldn't have been a hard one. I literally gave you the code, didn't I?
No, there wasn't any code.
Yeah, you said modify the MATLAB program.
Yeah, I was confused. There was no code given, so.
That didn't show up?
Yeah, the closest thing in the book was.
I'll just use some
Just finding
some
the
other things in the
normalized
book.
power.
Now, I thought.
I got the directivity, but none of the other ones, and so
Well,
I didn't even bother printing it out.
I wanna take a look at what you did. The whole thing with that code, that MATLAB, all right, that's a language that, you're supposed to become familiar with it. I think you use it regularly, don't you? I mean, are you supposed to?
I mean,
Some classes,
Which class uses it the most?
random.
random and control systems.
Oh, yeah, all right, so that's Dr. Hung. I could see him.
Boarding class with Dr. Wentworth, he loves MATLAB.
Well, MATLAB's, I'm gonna level with you, all right? People, they start with MATLAB, they don't like it because it's a learning curve. Like anything else, like a calculator, you spend time learning. I use MathCAD more than MATLAB for most assignments that are simple. But MATLAB, I'll tell you this, it is used everywhere, or they use Octave, which is very similar. And sometimes they can get away with Python, but it's called a prototyping language. It's a higher level language. They use that to create the first programs. Then when the programs work and they get the bugs out, they can take that Fortran, or they take MATLAB and turn it into C or Fortran 90, C++, and there's little conversion programs for that. And then those run very fast. They can compile them and they're super fast. But almost all the work that I do, if the first codes are done in MATLAB, and MATLAB has extensive libraries for special functions and stuff, so it's essential that you get familiar with it, because on the job, you're going to use Python or MATLAB, and virtually Python is a little more complicated, but it does the same thing MATLAB does, essentially. But not all the special tools are available to Python, though. The special packages. So it's essentially, it's really kind of important you get familiar with it. When I was at all the national labs, at NASA, all our stuff was done in MATLAB, everything. If you go to companies, generally speaking, they're going to be using either MATLAB or MATLAB, Octave, Python. Have you all used Python?
I've
You've
used
Python. If you use MATLAB though, right? MATLAB is very, it's very good to get familiar with it. Because if you think about it, isn't it a lot like C with for loops and all this? Only they have all the special functions and you don't have to have formatting, which is nice. Which is real nice. Yes. Did you have a question?
No, sir. I was just saying I've used the
Did you-
Octave before.
You what?
The Octave, it's just
Octave's
like a free
free.
version of MATLAB.
Yeah.
pretty
And
much.
Octave's slower, but I'm telling you this much, if it's small stuff, it's just as good, practically speaking. Now, there's no other questions about the homework we did? We basically went through some plots using the antenna factor, really. Really, it was what? The sine squared of n psi over 2 divided by a sine squared of psi over 2, right? And that was the antenna pattern that you get from arrays. That's it. And psi is just beta d, cosine of the angle theta between the actual array's direction and the direction of r. So it's the cosine of that angle. And it should have been fairly easy to do that. All right. There's one problem. Sometimes you get a divide by zero error, so you have to exclude that point. That's the only trouble you can have.
That's what.
What's that?
What's that? So what you just said is what I did, so I guess I did it right.
It should have been very hard, but I thought there was a MATLAB program that I gave you, and that's on me. All right, for today then, we're going to start with monopoles. We did dipoles, right? Monopole is just one antenna over a ground plane. In other words, you'll take a dipole, a halfway dipole, and you only use a quarter wavelength of wire above a ground plane to actually create the effects of a full wave dipole or full half-wave dipole. But let me go through, and before we start, talk about something, and this is called imaging. Write this down. Now, he has it in his book, but he doesn't really clarify it the way I'm about to. That's not going to lose its ink. So when I say imaging, it means this. if you have a ground plane, now this is real valuable when you're solving certain types of equations. The ground plane is something that allows charge to flow in and flow out. So if I have something at a height h above the ground plane and I put some charge plus q. Now here's what happens. That plus q charge will attract negative charge, and if you actually look, it will get in something that looks like this. You can in graduate school, we have to get the profile of that. That would be the charge density, rho s, only it would have a negative value. It would be the magnitude of the charge density. It's a peak right below there, and that should make sense. It would attract negative charge. But what really is a way we can model this effect is with imaging. And what we can say is, if we have plus q at this point, if we come down below the ground plane, we can put an image or minus q here. And then we can neglect the effects of the ground plane altogether, the charge density, and we're going to say this negative charge models the effect of all that accumulated negative charge density. Then if we come out at any range, let's just say this is R1, and a range here, R2, we can say the voltage here, V, at that range, whatever that point is, call it R1, comma, R2, whatever these respective range vectors are, is equal to simply Q plus over 4 pi epsilon naught divided by R1 minus Q, the same value, Q over 4 pi epsilon naught R2, or really, it's just Q over 4 pi epsilon naught, and then it's times 1 over magnitude of R1 minus 1 over magnitude of R2, and that is the voltage. Now, if you put R1 and R2 in terms of X, Y, Z, or any other coordinate system, you can actually come up with an equation for that. But this is how images work. So if there's a plus charge here, and you want the voltage, or you want the electric field or any other quantity related to it, above the ground plane, you'd simply say that this positive charge images a negative charge here at the same depth as the height above, and it has an opposite sign. Do you follow me on this? And this should make kind of intuitive sense. But the nice thing about this is, that equation right there is trivially simple compared to the way you would actually solve a ground plane problem. If you had a ground plane and there was no image, like so, and I had a positive charge here, then the way you would solve this problem is that del squared V equals 0. Do you remember what the name of that equation is? Anybody? The del squared V equals 0, where del squared V is minus rho V over epsilon. Does anybody remember that? That's called the Laplace's equation, right? It's Poisson's if it's minus rho V over epsilon, right? Well, when you solve this equation, you have a second order derivative. If it was in, say, spherical coordinates, it would be 1 over r squared. Don't write this down. Derivative with respect to r of r squared times dv dr plus other terms all equal to 0. Then you have to get the general solution. The only way you can solve this is by matching the boundary conditions that the tangent electric field everywhere on that ground plane 0. That's a work, all right? I remember doing that when I was in grad school. It takes some time. This is trivial, in my opinion. So that's the benefit of images. Yes, sir.
In the numerator, is that a Q or?
Yeah, it's just charge, Q
Okay.
over 4 pi epsilon, whatever charge is there. All right. Now, why is this important to us? Because here's what we deal with. We deal with antennas that inherently move current, but if you move current, you accumulate charge. Does this make sense? So let's look at it from that point of view. I'm going to put the ground plane down again. And now I'm going to take a little chunk of current and I'm going to move it this way. And we're going to assume this is going to have a current I, and it has a length L. Right? Now think about this just as a segment of current. What happens when current flows? If we had a short dipole there, y'all realize that this would be positive charge accumulated, and it would create negative charge or a lack of positive charge there. Do y'all agree with that? Now watch how it images. Say this is a height h. At a depth h, we could say that this positive would image a negative charge, right? and this would image a positive charge, right? You all agree with that? Wherever the negative is, below it's a positive, wherever the positive and negative, same exact depth. All right? Now what current would allow that to flow? If this current is traveling from left to right, this current would have to be traveling from right to left. And this is how currents image that are parallel to the surface of conductors. Does he show this in the book? He has a big A there, I think. A weird looking A. All right, this is easier to understand, I think. Follow me on this, guys? Now, what happens if you don't have currents flowing parallel, but you have currents that are vertical? Suppose I have N with length L and a center height H above this. Well, then I could say that the top part was getting a plus Q and the bottom part a minus Q. Do you all agree with that? Right? If you're putting current straight up, the top part accumulates positive, bottom part is going to really have a deficiency or negative charge. Agreed, everyone? All right, now how does it image? Well, if I come down a depth H, right, I would say what? This negative charge would image a positive charge here, and this positive charge would image a negative charge here. And what current would cause that? That would be a current flowing in the vertical direction. And that would be the image. Does that make sense to everybody? Take a look for a second, make sure you see it. You all see it or not? Right? Now, that means currents in the vertical direction or perpendicular to the conducting surface image in the same direction. Currents that are parallel image in opposite directions. So now what happens is, as we take a look at the typical example of, to really tell you if you understand it or not, if that's a ground plane, and if I have a current like this, call this height H1, call this height H2, and call this width W. So now I've got a current in this direction, I. How does it image? Well, you know the vertical component's the same direction, right? And the horizontal component is in the opposite direction, correct? So your image of this one, come down H1 again. You put a dot there, you draw it down this way. And what you would have is this. That would be the image. Does that make sense to everybody? Now, when you're calculating the radiated fields, I want you to understand something. There is no radiated field into the conductor. Beyond the ground plane, below the ground plane, there's no electric field. All the fields are radiated above the ground plane. Does everybody understand that? So now we look at some typical examples, and this is done all the time. These are how monopoles are really used, or created, how they're used. Anytime you have a large conducting surface, even sometimes not a large conducting surface, they don't have, like the aerial and the old car antennas, it doesn't have, it's not a dipole where it doesn't fold out and have the same, have a center feed and have a negative, have something down and something up, and then it's driven. What it is just what, an aerial straight up from your car, right? But your car's conducting, usually. So they use that conducting surface as a ground plane, and it causes a pseudo-dipole effect. So it looks like a monopole, but not quite. It's still useful. So now I go and I talk about monopoles and how the first one I'm going to talk about is, instead of a halfway dipole, it's going to be a quarter wave monopole, and the actual field chart the effects. Bless you. So this is going to be the quarter wave monopole. So first put your ground plane down here. And now above that ground plane, a short distance, I have an antenna that's lambda over 4 in length. And the way I actually drive it, I take a voltage source, ground the voltage source, and I take the positive lead and I feed it right there. And I ground the other. Now, you can see one advantage is it's half as long. Right? What would happen is there would be a current flowing here, and we know there's a current on the dipole, but we would have an image current here, and that image current would be of an extent of a length lambda over 4, and it would have the same current signature. If the current here looked like, it's a quarter wave dipole, it would look like the actual current distribution of a half wave dipole. So this effectively is the same as a half wave dipole in terms of how the radiated fields will be calculated. So if we go a distance away, call it r, and we're at an angle theta, we get the same exact fields we'd get from a full half-wave dipole. And we find that the E field here would be equal to J times 60 times I over R, and then it's going to be times e to the minus j beta r, and then it's going to be a funny function, cosine of pi over 2 cosine of theta, that f, in the a theta direction. And that would be the electric fields. Do y'all remember this is the equation for the fields from a half-wave dipole? Right, it has that cosine of pi over 2 cosine of theta argument in there, and it's got j 60 I over r e to the minus j beta r. Correct, class? I don't know if he says that explicitly, but that's what it is. Now, if that's the electric field, it's still the same electric field from the monopole, if it's a quarter wave. Got it? Keep going. What does that also mean? That means the P-Av would be the same as the half-wave dipole, correct, class? P-Av would just be equal to, I'm not going to calculate it exactly, 1/2 times magnitude of the E field squared over eta, and it would be in the AR direction, eta naught. So that means P-Av's the same. Another thing that means is that the normalized power density as a function of theta, phi, and r would be the same as a half-wave dipole. Do we all agree on that? There's a reason this is important. Agreed, class? All right, now, this is the thing that's important. If that normalized power is the same as a half-wave dipole, but it's radiating only in the upper hemisphere, say in the northern hemisphere. The southern hemisphere, there's no radiation, right? So when we calculate the gain, the directivity would be equal to 4 pi over the beam solid angle, right? Now what is that beam solid angle? Well, it would be 4 pi over the integral, double integral, of the normalized power density times r squared times sine of theta d phi. And from theta, it would only go from 0 to pi over 2, and phi would go to 0 to 2 pi. Now, what I'm going to say about this is, and if you want to, if it's normalized, you can actually get rid of that r and get rid of that r. So now it's just going to be an angular integration. This has a maximum value of 1 since it's normalized. But what you're going to find out when you do this integration, you see how it goes from 0 to pi over 2? It only goes from 0 to pi over 2. Not 0 to pi because there's no radiation below the actual ground plane. Does this make sense to everybody, class? But what does that automatically tell you? That this value will be 1/2 the value of a dipole, won't it? A full half-wave dipole? You all agree? If it's got the same exact normalized power pattern, but it's radiating only half the space, right? And so that means it's half the value of an actual dipole, the integration, which means that this directivity is actually 2 times the directivity of a half-wave dipole. A half-wave dipole was 1.64. So this is going to be what? 3.28? Yeah, 28. And that should be in there. That's the directivity. And for all intents and purposes, it's the gain as well, because usually the efficiency is about 99%. Now he has something like that in his book. So that talks about directivity. Now the other thing that's important, since the electric fields above the ground plane are identical and the power density identical to that of a half-wave dipole, there's no use in just going through the equations there because we've got them, right? They're before us. But there is one thing that is also different, and that's the radiation resistance. Now, I'm gonna make this argument with you. Listen to me, I don't have to go through an integration. Y'all agree that if the same electric field occurs out here that would occur for a half-wave dipole for a given current I, right? Y'all agree that the amount of power radiated in the upper plane would be the same as for the upper plane of a half-wave dipole, do you agree? And wouldn't that be the same power that would be radiated in the lower plane if there was a true half-wave dipole? So in a nutshell, I'm saying since it's only radiating up here, it's radiating half of the power that it would if it was a full half-wave dipole. Does that make sense? What that means is this. If I say P rad is equal to 1/2 for the monopole, I'll call it lambda over 4 monopole, is equal to 1/2 P rad for the dipole, the lambda over 2 dipole. That means the P radiated is going to be, if you remember for the half-wave dipole, they gave the power radiation formula, but they found out it was equal to I squared, right? And then it was times 73.2 ohms for the radiation resistance. Do y'all remember that, class? And it was actually times 1/2 this, by the way. That was equal to P rad. Well, if you take this quantity and divide it by 2, then you get the P rad for the quarter wave dipole. So it'd be 1/4 I squared times that. But, now let me get back to it. If the radiation resistance, if R rad for a half-wave dipole is 73.2 ohms, right? Correct, class? Do you remember that was 73.2 ohms for a half-wave? This is only the radiation. That doesn't include the J42.5, and I'll get to that in a second. Well, that would mean the radiation resistance for the monopole would be half that, because it's radiating at over half the space with the same current. So the radiation resistance for a monopole, that's lambda over 2 dipole. R rad for lambda over 4 monopole would be 73.2 divided by 2, and that's what, 36, right? 0.6 ohms. Now, something else I'm going to say, that for an exact half-wave dipole, you remember the Z, the total real radiation resistance with the radiation resistance plus the impedance was equal to 73.2 plus J 42.5. Do y'all remember that, ohms? That's what if it's an exactly a half-wave dipole, we didn't shorten it to whatever it was, 0.485 lambda, right? If it's exactly that, then the actual Z, and this is for a lambda over 2 dipole, the Z for the lambda over 4 monopole is simply half that. So it's 73.2 plus J 42.5 divided by 2, and that's what, 36, right? 0.6 plus J 21.25 ohms, and that is the actual impedance of the lambda over 4 monopole. That's how you do it. Okay? Now we can go through other antennas but that are monopole, or they're just over a ground plane. The thing I'm going to caution you about is this. Anytime you have dipoles, this is the technique you use. But I have to show you one thing. It's not in his book, but you need to understand it. This is something that has to do with electromagnetic compatibility, and it's important. Now, if you have a current I like this of length L, and it's at a height H, and it images in the opposite direction at a height below that H, you can see one thing happening. Now, the electric fields from these two don't add directly. What you have, because you have a phase difference, right? It's not like the dipole antennas where the image itself the image on a monopole creates the dipole fields, right? Here, what you need to do is if you want the electric field, let's just get the electric field from a center point out here, a distance r away, and assume L is much, much less than lambda over, or much, much less than lambda. So this is a short dipole. Can you all understand what I'm doing here, class? Please follow me. This isn't in the book. What I want to know, perpendicular to the ground plane, if I have a short dipole above there, it's going to image like this, right? Now, what are the fields above here? Well, the fields would be that of this antenna plus the fields of that antenna, right? So now we look first at the fields of a short dipole. If I have a short dipole like this, and I come out perpendicular to it at a distance r away, and this has a current I, it has a length L, then I know my electric field here would be equal to, and it would be in this direction, this E field would be equal to J eta beta over 4 pi divided by R times e to the minus J beta R, and it would be times I, and then it would be times sine of theta, but since theta is 90 degrees, it's 1, correct? Right? So that would be the field. It would be in this direction. Now note, if I want the fields here, and this has a height h, I would say the total field right here at a distance r, it's going to be the sum of the field from this antenna right here. I'll call this, actually it's this way. I'll call this E1, and the fields from this image, which would be E2. So I can put down the J eta beta. They're always, both of these are going to have J eta beta over 4 pi. Both of them are going to have I, same thing. Now the difference, the 1 over R, let me make a statement here. I'm going to say 1 over R is about equal to 1 over R plus or minus H. That H is not significant, it's small. So R is a long ways away, okay? So I can put the R here. But now I have this. I have the first one, which is e to the minus J beta quantity R minus H. And then, since this field is in the opposite direction, it's minus e to the minus J beta, and then it's R plus H. Follow me on this. This term, remember, this is the general equation for field. Now, if I'm near, if I'm that top eye, you'll notice one thing, it's minus J beta R. Well, R is going to be R minus H, correct, class? Y'all see what I've done here? No? Think about it. What's this distance from here to here? Isn't it this distance from the ground plane there, which I'm calling R minus H, class? Isn't it? All right, so that's what goes here. But the next one has a current going in the opposite direction, the image, right? So it's going to be e to the minus J beta, and then it's R plus H. Do you all see this? Because it's further away, right? Yes, sir.
Is it not R plus 2H?
Well, I'm measuring R from here, from the ground, right? So it's either plus H or minus H.
Oh, I see, okay.
Okay, I'm measuring it right from here, from the ground plane. Does this make sense? Okay? You're looking at me like you don't believe me. Or looking at the board like you don't believe me. Are you okay with that or not?
I think I got it.
You all see what I'm doing here, really? I'm just adding the fields from 2 wires that are short. And it's right above it. You can do it yourself later. Now, what I'm going to do with this, though, and some of you can see how the e to the minus J beta R sucks out? So I'm going to go ahead and do that. You don't have to write this down yet, but you can. Then I'm going to put I over 4 pi R, because I'm a long ways away, times e to the minus J beta R. And then I have this little guy. Then I have e to the J beta R, right, because the minus sign is. And then I have what? Minus e to the minus J beta R, right? Now what can I do with that? Anybody? Somebody I bet you gets it. Well, this is where the minute you see a couple of things with exponentials, you always think of this. I know that the sine of theta is e to the j theta minus e to the minus j theta over 2j. And I know cosine of theta is equal to e to the plus j theta plus e to the minus j theta, right, over 2, right? And which one fits there? Isn't that what we got here? Don't we really have, if I put the 2j here, can y'all see how that is virtually the same thing as that, only theta is beta r? Y'all see that, class? Why don't you, can you see it back there? Or not?
Say it again.
Okay. Oh, you're listening. Can you see, you understand these are,
Okay, yeah.
and you got, so this is what I'm about to do. Is the world's, what's the game? What are you listening to?
Oh, it's just background.
Oh, never mind. I thought there was a sporting event that's going on. Is College World Series on right now?
Tonight, I think.
Oh. Okay. All right, now what I'm gonna do, just for the sake of being brief, I'm just gonna say this is gonna be 2j, right? And then it's gonna be times the sine of beta h. Do y'all agree with that? I put the 2j in there. One thing you can see about this is that 2 and that 4 can get a cancellation. The j times j is going to be minus, right? But it doesn't matter because we care about magnitude. So really what happens here is let's get rid of the j's. We can put a minus sign, but it doesn't matter. Get rid of the 2. And now that's it, right? Now take note of this. What happens as h goes to 0? Sine of 0. What is the sine of 0? 0. So as the distance above that ground plane gets real small, all of a sudden there ain't no fields radiated. That should make sense because the ground plane shorts it out. But if you put out beta as simply 2 pi over lambda, and then you put the length of the antenna in terms of L over lambda, now you can do something with that. And furthermore, you can make the argument that if this is small in terms of radians, then the sine of x is about x. So you can simply put down 2 pi over lambda times the length of the line in lambda. Follow me? Or you could just put it beta times L. Either one. Agreed, class? Just remember that. And this is a good thing to remember because when you're going to find out that a lot of things you deal with have to do with wires over ground planes radiating. It just happens to be an inevitable fact of life in this world. And well, I can't do it here because frankly there's no exposed wires, but if I was some of the other things, actually a long extension cord, it's not one of these coax cables. I'm talking about a real extension cord. You just lift it above a ground plane. You basically got 2 wires that are parallel to it that are imaging opposite current directions and opposite to themselves. So the radiate or the actual electric field from those things can be calculated. It's kind of interesting to do something like that once. So that's what happens when you get currents that are parallel to ground planes. I'm going to give you a couple problems on that. Remember, this isn't in the book, so good notes on this one. It's important. All right, next, covered monopole. Covered that. Now we're going to do something, and this is kind of finishing up this chapter. I was basically done with it, not quite. Now we're going to do radar. Now I like radar because I teach the radar course. I've dealt with radars, done work with radar. I'm by no means an expert, I wish I was, but I like it a lot. And I'll tell you one other thing about radar. Radar is just one system we use to sense what's around us in our environment. Radar is extremely important because day or night, it works. And it's a way of finding out what's in front of you. Now, bats have their own version of it. It's a sonar, it's an echo thing, but they know exactly what they're going, where they're going, even if there's absolutely zero light. And they know what's going on because they have an effective sonar. Well, radar is just like sonar, only instead of using sound waves, they use electromagnetic waves to bounce off things. And radars are going to become ever so popular, efficient radars that you can do more than just interrogate the region, where you can bury signals, say communication signals within the radar signature. The same exact amplifier that you're using to amplify the radar signal you can embed a communication signaling, so you all have only one transmitting antenna fit. This is important. It's especially important where drones are involved. Now, drone technologies, you've probably heard of it all over there. Really, your mail is probably going to be delivered by a drone in the future. You're going to have a little pad where it lands and drops off your mail, packages of certain sizes, and they're doing tests of this. The problem with any drone and anything, even if it has GPS system stuff, is a non-compliant aircraft or a tree that falls where it's not supposed to be, or something unexpected. A bird flies in, some eagle gets mad, something like that. So if you have a radar, you can build in a small amount of an artificial intelligence. It's easy, and they can have a collision avoidance system to prevent those kind of collisions for these drones. Drones are very, very popular. I don't have, if you have any clue, if you've been looking at the predictions for technologies, in the future, I mean, Google and Amazon, I understand, have invested huge amounts in this, as well as the governments of the world, because they know that is the cheapest, most effective way to get packages from point A to point B over a relatively short range. Your mail carrier doesn't really need to be a mail carrier. Your UPS guy or FedEx guy, he needs to come park his van in an area and let his drones deliver everything to that area, and then they gather them back and take off. And that's a reality. It'll really make it efficient, and then there'll be all sorts of problems that are associated with that. And the primary problem always is like hanging wires, stuff like that. You know, it's hard to see them, but a radar can see it. As long as it's not just a clothesline, they can see things that got metal in it. You know, most wires that are hanging around still have metal, they're not fibers like that. So remember that. So here's how radar works. I wish there was a way to prevent that. Radar is really radio and ranging. Radar started in World War II. It was developed and came into its own during the bombing of Britain. They developed a very primitive radar fence, and it prevented really the British from Britain from being beaten by the Germans at that time. If they didn't have radar, they'd have lost that no problem. We wouldn't have had any country left, but at least from what I've read. So what is radar in a nutshell, the simple form? Here's how it works. I have a transmitter. I'm going to do a monostatic radar. It means it has the same transmitter and receiver. Monostatic radar. Now what it is I'm going to have a signal that I send from my radar unit, an electric field. It comes out and it strikes a target at a range R. So the target at some range R. Now when the waveform hits the target, it also comes back, goes the same distance R, and then the receiver receives it back. So the real way a radar works, if you looked at the power that's being sent versus time. So this is going to be the power versus time on a radar signature. It looks something like this. It's on, it's off. And it's off for a length of time called a period, or the pulse repetition interval. And that's sometimes PRI. Pulse repetition interval is 1 over the pulse repetition frequency. And this T is usually of the order of milliseconds. It can be less, and then it repeats itself. So follow me on this. Power on, pulse is sent, right? Then it shuts down, right? Now it listens. for anything that comes back. It's looking for something coming back. This part is called the listening, or really, this is where it becomes a receiver. It listens. Here is where it's transmitting. Okay? I'm just trying to give you an idea. So the way a radar works is, it's sort of like if you're by a place where there's some echo, and let's say it's a mountain range, and you yell, then you don't yell, and you listen for an echo return. Then you yell again, and you can listen for an echo return. But the thing you have to make sure is that when you yell, there isn't an echo return in progress, or you can't hear it. So that's why this length of time from here to here becomes a critical aspect of radar that we'll talk about later. But now we get into the basics of radar in terms of the signal, how much signal is actually recovered. Now follow me. If I have just an antenna and I'm transmitting here, I have an average power density at any given range of the transmitted power, total transmitted power, over 4 pi r squared times the actual gain of the transmitter. Do you agree with me? That's the power density that would be in the waveform of a transmitted wave. And you have PT as your power density, and the gain is G. Agreed, class? Now it goes out and it strikes this target. And that target echoes back a certain amount of power. So the amount of power that's actually reflected, P reflected, power reflected is equal to the power density, PF, times something called the radar cross section. The target has something called the radar cross section. And sigma is often termed the RCS, radar cross section of a target. So this is the total amount of power reflected, and it is in watts. Please make sure you write that down. And that should make sense to you. If you have a power density of so many watts per meter squared, and it hits something with a certain RCS, and our radar cross section is in meters squared, better put that down, this is in meters squared, then what results is watts, right? Watts per meter squared times meter squared is watts. Now, this sigma, by the way, can be a function of the angle that actually this thing hits it. So if you think about this, if this is the bore side, it may be a function of some angle, but I don't want to drift into that territory. Now, all that power is going to be reflected without any gain feature, unless the gain is included in this sigma value. It's going to be reflected isotropically. Do you follow me on that? So now I come over here and I say P reflected is equal to the total power, I should say power reflected, P ref density, I'll just call it P reflected small ref. Here is going to be sigma times P, the average power, and then it's over 4 pi r squared. Why r squared? Because it's reflected, and now it's going to come back and hit this. Follow me? So the way it works, I have a power transmitted, P transmitted times gain over 4 pi r squared that hits this, multiplied by sigma, that's the total power reflected. And how much is reflected back here? Where it's going to be that total power divided by 4 pi r squared, because there isn't that gain effect. Do you understand, class? And any focusing ability of this would be included in sigma. All right, it would increase its value if there was any focusing. So that's the amount of power reflected that's coming back and striking this antenna. Now we need to find the amount of power the antenna catches. And that means how electrically big it is, or the area, or aperture. So now we can say that the power received by the antenna, power received would be equal to this power reflected times the area. Do you remember what the aperture is in terms of, or the gain, the area of the antenna in terms of gain? Anybody?
Lambda squared G over.
That's exactly right. It's lambda squared over 4 pi times the gain of the antenna. And this would be gain of transmitter too, because they're the same. And that would be the amount of power received. Now I'm going to give you one single equation in a second. But you follow with the thought process. You got transmitted power density, reflected power density, and then reflected power retrieved. All right, now, how much is that? So we can say here that P received, please watch this, is going to be the transmitted power, P tran, times the gain of the transmitter over 4 pi r squared. Y'all agree that's the transmitted power, right? Density, power density. Then I take that and I multiply it by sigma. Right? Now that's the amount of power reflected. Agree? Sigma is the RCS. Agree, class? Now I take that and I have to divide that again by 4 pi r squared. Because now that's the amount of power that's actually incident on the antenna that transmitted from us. Agree? Then I have to take that and multiply it by lambda squared over 4 pi times the gain of the transmitter again. Correct, class? Now you can see that 4 pi occurs 3 times in the denominator. And you can see it's r squared times squared, r squared, or r to the 4th. So this equation can be reduced to this. You can put P received over P transmitted is simply equal to gain of the transmitter times gain of the receiver times sigma times lambda squared over the quantity 4 pi cubed r to the 4th, and lo and behold, you have what's called the radar range equation. It's RRE, radar range equation. And what that is a simple relationship of recovered power to transmitted power for one short duration pulse. Does that make sense to everybody? Now he has that in his book, doesn't he?
Yeah.
When I teach radar, this is one of the first things I teach is that equation. It's very simple, very fundamental. There's a lot of other stuff I teach. Dr. Wentworth has some of it. But I'm going to cover some of the aspects. That's the basics of power recovery from a single radar pulse. And that's important to understand. Because the way that they actually gauge whether there is or isn't a target out there is as they listen, when all of a sudden the power density that's being recovered at that frequency goes above a certain threshold, they say there's a target. And they can get the range by the timing delay. Right? So that's sort of a primitive way to think about radar. Next. The real thing that was hard with radar when it first came out was to get a source of power that had a very, very stable local oscillator. The frequency can't vary much at all. If it does, it's useless basically. So they spent a lot of time creating devices. Do you know what a magnetron is? Have you ever heard that term? Magnetrons and some other things, standing wave tubes. Magnetron is basically this, and I think you can understand this. It's a resonant cavity. Why is that important? Well, think about something, let's do the mechanical analog. Suppose I have a metal pipe that's of a certain length, and it's solid, hollow metal pipe, capped at one end, and I take a hammer and I hit it, and I listen. I hear bing, and then it rings down, right? I hit it again, same exact frequency, it rings that. The resonance of that pipe is the thing that is really the thing that dictates the frequency, right? Well, with a magnetron, you basically hit a cavity that has a magnetic field with a burst of electrons. And what they do is kick it, in a sense, and it creates electromagnetic energy that's going to bounce around and have a certain characteristic frequency, the resonant frequency that I want. And that energy can be sucked out by a little threaded antenna in there, and then it rings down. So it's ringing, say, at a very fast rate, and you would think of it as basically the tone becoming less and less obvious when a ring down of a bell or something like that. And that it sucks that energy out of a magnetron. Then they have to kick it again, and it does the same thing. Do you follow me on this? That's sort of the way a magnetron works, but it's a way of generating very high power microwave. And that was something that was researched at MIT at a place they call the radiation labs to throw off the Germans. Because radiation always means nuclear weapons, but in that case it had to do with radar. and the British did a lot of development. We had a fellow here named Marshall Harnell that was on that project. He taught till he was 95 years old. He's passed away, but he was an amazing guy. I learned a lot from him. He was involved in the first space program, in developing the communication stuff that went on the moon. He was a wealth of knowledge. The crazy thing about it was that Marshall Harnell was somebody that actually remembers fragments of the First World War. That's how old the guy was. And his mom was a first aid worker for the Germans. He was a Red Cross worker. And I don't think his dad was a Frenchman, so basically they were fighting against each other. He had a great story. All right, now getting back to this with radar. There's one other aspect of radar we have to talk about, and that is called, there's several, the Doppler frequency. Well, Doppler shift, or Doppler frequency. So what is that? I'm going to do it the way Dr. Wentworth does. This isn't true for the relativistic type, but it's good enough for now. This is the gain of the transmitter. You put in a certain power density, transmitted power density, it shoots it off, and it goes a distance r, and it hits a target. Now, if this target is moving such that a component of the velocity is in the direction toward or directly away from the antenna, the radial direction, let's say it has a velocity VR. Make that a little bigger. V sub r. It's either going at it or not. With me on this? Now what we're going to do is this. We're going to say, well, how far does the actual, or what path length does the signal travel over one pulse to recovery? Well, it would travel over 2r. Do you agree with that? It has to go out a distance r, hit the thing, and reflect back, right? Y'all with me on this class?
Yeah.
So now we say, because we want a Doppler shift, and the way we're going to do it is we're going to get how many wavelengths are involved first. So if I divide this by the number of wavelengths in the path, say a wavelength is a meter and it's 10 meters away, that would be 20 divided by 1, or it would be 20. Do you follow me on this? But now we need a radian number. So if we multiply this by 2 pi, now I know how many radians are involved in that path. I know how many wavelengths. Each wavelength is 2 pi radians, isn't it? Now I know the total number of radians the signal went by. And then I can say, let me write that a little, I'll write it over here. That's really 4 pi r over lambda. And that's the actual phase of the wave. Think about that, the amount of phase that the actual wave underwent, or phase change. Now if I take a derivative of this phase with respect to r, with respect to time, not r, then I get 4 pi over lambda times dr dt, or the rate of change of r with respect to t. Are you with me? Well, the rate of change of distance with respect to time is velocity, isn't it? And that's radial velocity. So I can say that this is really equal to 4 pi over lambda times v sub r. That's radial velocity. And that's equal to the rate of change of theta with respect to t, or omega, and put a sub d there. The d means it's a Doppler frequency. It's created, this frequency is something associated with the rate of change of the distance, or the velocity. Well, the Doppler frequency in radians can be also interpreted in Doppler frequency in hertz, and that's 2 pi times f Doppler. And then we can say what that also means is that f Doppler, or the Doppler shift for non-relativistic movement, would be simply, well, that's 2 pi, 4 pi, I get 2 over lambda times VR, and that's the Doppler shift right there. Now lambda is the free space wavelength. I'm going to put it in terms of something else in one second. Y'all follow me on this? This is the one I remember. You can cut it, land the knot there. Now, the way Dr. Wentworth will have this, he'll have F Doppler equal to 2, and then wavelength is C over F. So he'll have C here, and then he'll have F naught. And that's the radar transmitting frequency times VR. And that's the Doppler shift that would occur. Now, how Doppler shift works is this. If I'm transmitting a 10, or say a 10 gigahertz signal, and I calculate a Doppler shift of 100 megahertz, if the thing's coming at me, it increases the frequency. So it would be 10 gigahertz plus 100 megahertz would be the actual frequency that I'm receiving. If it's leaving me, then it's going to be 10 gigahertz minus 100 megahertz. Follow me on that, everyone? So you have to remember that. It's either going to be an increase or a decrease in the actual frequency. As a matter of fact, remember when you had, have you been all around car races or anything? Even without that. When a car's coming through you, what do you hear? Right? When it's going away from you, right? That's a Doppler shift. That's it. So it's kind of important that you at least appreciate that. Remember, with Doppler shift, it's coming at you, increase in frequency, away from you, decrease. And it's always the center frequency that moves, all right? It's the frequency you receive. 10 gigahertz, think about this. We're going to calculate the Doppler shift for a radar that's typical, let's do an X-band police radar. So the actual transmitting frequency for old radars, not used anymore, it was X-band, it was about 10 gigahertz. Right? So if we take a look at that when we go on to get the Doppler shift, if you're going, say, 100 miles an hour, you probably get a ticket for going 100 miles an hour anywhere in Alabama. I don't think it's legal unless it's on a track. All right, well, let's calculate 100 miles an hour in meters per second. You've got Google, right? You can do it. Well, we could go through the rigmarole, miles 5,280 feet, right? And then, so we could calculate feet per hour, then we have to divide by, let's see, 60 seconds times 60 by 3,600. We could go through this, but can you, what's that?
Meters per second.
What?
Meters per second, 44.7.
All right, so this is 44.7 meters per second. That doesn't seem all that fast, but it is. 100 miles an hour is fast. So what's the Doppler shift for this? Well, that's 2 times 10 gig, or 10 to the 10th, right? Over C is 3 times 10 to the 8th. And then it's times the velocity, which is, call it 45. So what's that Doppler shift going to be? I got 10 to the 8th and the 10 to the 10th, that's 100. So 45 times 2 is 90. Divided by 3 is 30, so it looks like 3,000 hertz, right? So it's 3,000 hertz. Now I want you to notice this. We're transmitting 10 gigahertz, and we're only getting a shift of 3,000 hertz. Is that measurable? Not easily. Not easily at all. And the way they have to, this is where I get into I could spend some time on this. This is where signal processing becomes handy. Now, what if we could remove the high frequency component from that? Well, that'd be a benefit. How could you remove the high frequency component? Does anybody remember? Well, you remember, did you have heterodyning? Did you have anything? Suppose you had a signal coming back at you, it's like 10 gigahertz signal, right? You could represent it as cosine of 2 pi times 10 to the 10th t plus some phase angle, right? If that's coming back at you, but suppose that it's also being modulated in its amplitude. Suppose it's got an A of t times that cosine of 2 pi times 10 gigahertz t plus a phase angle. And we want to recover just the amplitude. What do? Well, we multiply it by another thing that's got cosine of 2 pi times 10 gigahertz t, right? Because then you get the sum of the difference frequencies. Do you all remember this? That's when we did didn't you have a radio lab here? All right, well, when you get some of the difference frequency, then you work at what's called the low frequency or baseband. Now you're working at just the frequency associated with the shift, and that's later on. Anyway, that's not a lot, is what I'm saying. And if you look in the spectrum analyzer, if you try to look at the difference, an actual signal in a spectrum analyzer, if this is power density versus frequency here, you're going to get something where you got a threshold, and then you're going to see a crisp little peak like this at your operational frequency F0. Now, when that shifts, if it shifts of the order of maybe 5%, you can notice the shift. But you can't notice a shift if it's 0.0001%. It just doesn't happen. The only way you do that is move all this crap down right here, where it's now at 0 frequency. Now we can see the shift, and that's what we do. And I'm not, he doesn't do it in his book. I'm not going to do it right now, but you have to understand it's not a trivial thing to do that. And that's why you need a very stable local oscillator in order to get this. And by the way, all radars of importance that are I shouldn't say all, most radars today that are of importance are moving target indicators. They don't really care about how far away something is. They care about, well, they do, but they really care about how fast it's moving at them, because that's the key. So moving target indicators are always looking at the Doppler shift, and that's why they're so important. Does everybody understand that? Keep that in mind, because people want to avoid problems. And if something's coming right at you at a great velocity, two things can be happening. You can be flying, and the thing can be stationary. That means the rate of closure looks like you're coming at it, but it doesn't matter with Doppler signature. Or you can be stationary, it can come at you, or both, a little of both. But you always want the rate that something's coming at you. You care little a lot of times about how far, what else is out there that's not moving. It's what's coming at me that I care about. And that's the same with a boat moving. You know, I don't have any kind of radar on my boat because I don't go out. I'm not somebody that's going off the coast of Florida or anything like that, or Alabama. But if I was, I'd want one. And those radars, there's another type that I'm just going to tell you about. It's a weather radar, because another very important thing to know about are any cells, storm cells in your area. And those kind of things have they're more sophisticated, more expensive, but they have a way of taking a look at the Doppler radar signatures inside the actual cloud and getting, and that's real important. They also can get, the relative reflectivity gives you an idea of how heavy the rain is. You see this on the weather guys, right? They always show them, they have it color coded. You always want to color code because intensity maps that are gray and white are very hard to read in daylight. I don't know if you realize that. You ever look at your phone in bright sun and stuff like this? The only way you can tell what's going on is because of the color resolution. And with weather radars and even depth finders, almost all of them are they're not grayscale. They have a color scheme. So red's usually intense, and blue is very unintense kind of deal. And that's the same way it is for weather radars. If I have time, I'll spend a little more time with radar. There's some really interesting stuff I'd like to show you. So that's radar in a nutshell in his book. And then the next thing we're going to do, I'll tell you what I'm going to do at the end of this course. I think I'll have time. I'm going to go through and I'll go a little more into detail on radar that I think would be applicable for you guys, because you're about to enter your senior year, right? If you like radar, think about taking the course. You'd get a lot out of it. And from what I've been told, a lot of the people around Huntsville and certain other areas, they're looking for people that have been exposed to radar. The course I teach or other courses Dave Beverly might teach. It's something that will benefit you. Now the next thing we're going to talk about, strange enough, is another course I teach, and that's electromagnetic compatibility. That's chapter 9. Now I want to tell you about this before I get into it. It's really electromagnetic interference and compatibility. And I got to just give you a background on this. When you create anything, it's based on any kind of standard electronic components. It can be a VLSI chip, it can be a controller for a motor. What you have, almost inevitably, is a digital clock. All right, now that digital clock is something that's used by everything. It's something that literally starts the JK flip-flops doing their work and turns on gates and off gates. It's used extensively. Whenever you have a clock, it turns on, it forces current to move down. When it turns off, the current's going to dissipate, but the current's going to have a characteristic frequency of that digital clock. Now, all those short wires are really short antennas that are radiating. They're radiating all around to the device, their device, and also to other devices in the area. And the problem with this is that causes electromagnetic interference. And there's all sorts of rules called, that's the FCC, the Federal Communications Group, that dictates the levels of signals you can radiate at different frequencies. And it's very, very important that your equipment matches that. Otherwise, you get all sorts of catastrophic failures. Let me just give you an example of the worst one that I know in the modern era. And I'll tell you about two others before I start this one. Do you know who John McCain is, Senator John McCain? Well, he flew a Phantom jet in the Vietnam War. And his jet was equipped with missiles. I don't know if you know the story. It was a I'm trying to think of the name, I just heard it today. It's not a Sideliner, it's a Zoomy missile. And a Zoomy missile has something called a squib. It's the thing that electrically ignites the detonate. It's really the powder charge that goes off that causes the primary detonation, so the rocket turns on and goes. Well, the problem is that they had, I believe it was an Army helicopter on board, and it keyed its microphone. Now, when it keyed its microphone, it sent an electromagnetic signal that was the same, that basically overpowered the squib's preventative measures, and it turned it on. Have you ever gone by a region that said turn your CB radios off? Have you ever seen these around here? Anybody? In Alabama? They changed the way they do business a while ago, but it used to be people with dynamite would put a detonator in there, and they have it down in a mine or something, and then they had this cord that they pull back and they push the plunger. Well, the problem is that long cord is a huge antenna. And so if you keyed your mic on a CB, if it was an illegal one, especially where you had more than 5 watts of power, it could easily detonate that thing and somebody could get killed. So they tell you, shut off your CB radios. Has anybody ever seen this? Nobody? It happened. I remember you seeing these signs all the time. Well, something like that happened. And the guy keyed his mic on the copter. This is the story I remember, and it's what happened. McCain threw the rocket or missile on his Phantom jet, triggered, fired into the tail end of a plane, another Phantom jet, blew that thing up there, started a chain reaction, and almost sank the ship, killed something like 500 sailors. It was horrific. It was caused by EMI. There's other events, and I'm going to just tell you about two because you'll get a kick out of a couple. Long ago, cars didn't have electronic ignitions. They had things called points. Does anybody ever remember points? Ever hear of that? Points are things that are mechanically closing and opening. All right, it was based on the actual position and degrees of your shaft, the camshaft. So back in those days, doesn't matter how much EMI, your car always works. Doesn't matter. Lightning could hit it, it would work. You couldn't destroy it because it was points. It was mechanically opening and shutting with switches. Then we went to electronic fire, like yours has on mine. So about that time was 1987 when they did this. 88, 87, 88. Let me go. 86, 87, 88. So people are buying cars that work at Dogburn, Virginia. And I happened to be going there in 87 to work as I was a professor here, but work at the summer as for the Naval Surface Warfare Center in Dogburn, Virginia. Briggs was with me. And we were told this story that when they bought these new cars and parked in the lot, they also parked them near what's called the Empress Test Facility, which is something that simulates the electromagnetic signature from a nuclear weapon. Out in Chesapeake, a quarter mile away, in a parking lot are their cars. They come back after testing, and all the new cars don't start. They're wondering what's going on, lousy cars. So after they spent money and stuff, another test is scheduled for about a month and a half, 2 months away. And I'm just guessing, I don't remember how many months. They do a test, what happens? They all fail again. What is the two things they had in common? Test failure. And they figured out that their electronic ignitions were they were literally just breaking down the gates on their FETs, the FET transistors, and destroying those modules. And then they got smart and they moved the parking lot for all these cars into an area that basically had enough metal in front of it that it couldn't it couldn't cause failure because of that. That was one AMI thing I tell you about. The other is kind of funny. Now remember, I don't advise you to do any of this. Because I got put on record one time of saying something and a kid literally said, oh, that sounds like a good idea. He did it, and it had to do with trains, and it had to do with the train tracks being a transmission line. Now, if you take a car battery, don't ever do this. And you take and clamp down one lead on one track and then touch the other a couple times, you'll send a wave down there. And if you look at an oscilloscope with fast enough timing, you'll see little blips coming back where the reflected wave's coming up. I don't know if this is true or not, but it's a great story the way he told it. It's like, well, when you do it, you know what else happens? Crossing gates start coming down. And there's all sorts of fun, because they use those train tracks to communicate information, electrically signaling. Oh boy, that's a great thing. How many laws have we broke here? I mean, I'm sure there's international commerce laws involved too. And that was that's when I started always qualifying anything I say that has to do with something like this with, don't do this. So don't do this, I don't. Anyway, you know what a CB radio is, don't you? All right. Well, truckers are notorious for getting these linear amplifiers, so they're more than 5 watts of power, so they can talk a long way. And these guys, you know, they don't have nothing to do all day. They've got to find a release, and they have all sorts of gadgets to do this with them. So, truckers coming down the highway, and there's a dump truck. Now remember what I told you, that a lot of stuff went from really mechanical stuff, mechanical points and all that stuff, mechanical systems to digital systems, right? Or to at least solid state systems. So this guy keys his mic, and a dump truck with a full load down the highway starts opening up and dumping its load, unbeknownst to the truck driver. And I see it done. Stuff like this was routine back in the old days. It's funny, I'm thinking about it. What if you were the car behind that guy? And you're driving through piles of dirt and stuff like this. That kind of stuff was happening routine. Then they had the FCC clamp down with all their laws. Now, from now on, if you can do this, you can do anything illegally, but I mean, legally you can only do this and this and this. And so products don't cause bizarre behavior of other products from now on. That's by the FCC. Most of it is radiated emissions. There's something called, conducted emissions is through like those power lines. If I plug in a device, believe it or not, any high frequency signal that gets in there still transmits down. That's 60 hertz. But if you're at 100 kilohertz or 200 kilohertz, that's a great conductor of that. And it'll go to everywhere in the building. So if your equipment, you have sensitive equipment that's got a problem at those frequencies, it'll probably have a real problem when you're transmitting it that. But we did this as a project. I don't mean to be wasting time, but I gotta set the stage for some of the stuff. It's not gonna come up now, but will. So when I was in college, what we did for a project, we had several of these major projects, senior projects. You have one capstone. We had like 4 or 5 big ones. What we did is we used that, the wall outlet, as our communication link to put out 2 channels of FM transmission at 100 kilohertz and 200 kilohertz. One of those channels was one stereo channel, the other was the other stereo channel. Then we could plug into the wall anywhere something that would extract those signals, but we also had a power source, so we could use that and have an amplifier right there, and then a speaker system. Now, who would benefit from that? Fraternities, because fraternities have nuts around them. And what you want to do is, you don't want your expensive speakers and stuff like that to get mauled by a bunch of bumps. You put all the expensive stereo equipment in the house, and then you go get, and there were, I didn't actually see these concrete speakers, and you put, these wire mesh things in the front of them, and you have your amplifier on there, so that you extract your signal, amplify it, and then go ahead and put it into the speaker. It's very cheap to build speakers, actually, if you know what you're doing. You can, but then now they're bulletproof in a sense. They can't destroy them. So the idea was all the expensive stereo equipment and stuff like this is in the house. They can take these things, plug them in anywhere. They got one channel of sound there. They could have another channel at the back of the room, and now they got a party. And that was sort of the thing that drove us. And we did that. And by the way, we also built, I think it was a 100-watt amplifier. It was real low distortion, very cheaply. If you're an electrical engineer and you go through the program and you think about building your own stereo equipment, or really in this case, it's really going to be home entertainment systems, the 5-in-1 thing, or it's 5-channel sound where you get a subwoofer. You can make an incredible speaker system and stereo system. Well, I should say a sound system, very cheaply and inefficient. It can be a very efficient thing. You know how much they cost nowadays, right? Over $1,000 in some cases. You can do that for pennies on the dollar, man. You can make that for probably $50, $60 if you're willing to do a little work. The big thing was speakers. The amplifying stuff you guys can make very easily. You know the best thing to make speakers out of? Go ahead and find old, have you ever seen these real thick cardboard tubes that are used to contain stuff? What you want is something circular and you want something thick. It can be made of wood. And then you can take that and you can use that for your subwoofer. And for the actual box speakers, man, you can make that with this board right here. Just find old material and you can carve it and get low efficiency speakers online. It's been a long time since I've done that stuff. Dr. Riggs has done some of this, and if you're ever interested, talk to him about speakers, because he used to be a he was a sound, somebody that loved really high-end, high-fidelity sound. I'm over, guys. I didn't get into that, but I'm going to next time. All right. Is everybody sleepy here in the afternoon?
It's only because most of us came from comm systems.
Did you have a test?
No, just.
It's
It's
lab
just-
based and it's kind of
It's just a
strenuous.
struggle.
Comm systems. What are you guys doing tonight?
I don't know, I think he's doing it different for us. We just do lab experiments every day.